Hello everybody, I'm Eloi from Savoir-faire Linux, and today I'm gonna present you the SEAPATH project from LF Energy with Robin Massink from Alliander. So the SEAPATH project is a virtualization for real-time power grid substation automation. This project is a collaboration between two major European electricity players. RTE, which is an electricity transmission system operator in France. RTE is managing 100,000 kilometers of high voltage lines and is one of the biggest players in Europe. Alliander is a distribution system operator in the Netherlands and is a precursor of virtualized substation automation system. Savoir-faire Linux is a Canadian and French company specialized in open source product development. So we see right now a big energy transition with more distributed system with renewable energy sources. There is a dynamic electricity flow and a growing number of third parties. So we need to adapt the grid control architectures to a more distributed control system, a more dynamic and adaptive automation functions, and we need to provide increased data management. So right now, a digital substation looks like this. We have a different bay. Each bay is linked to one high voltage line, and its job is basically to monitor, protect, and control it. Each bay includes individual physical equipment for sensor, SCADA, or protection. And some of the equipment is of course linked to the network through a LAN. The goal of the SEAPATH project is to basically remove all the equipments and to replace that by applications. We want also to share a common platform, and of course we need to provide more connectivity features to be able to easily control and maintain all this equipment. So this slide shows the virtualization for new grid control architecture. Each bay will be basically re-engineered into a power grid substation. Virtualization will be used for each substation on top of hypervisors, so that we can share a set of hypervisors which host virtual machines and containers. We can, and it's very important, reproduce this setup very easily, even in a completely fake environment with fake data. And we can so open the setup to new players or new contributors without requiring a big equipment. And of course we can develop, test and push new features into the production very easily thanks to this virtualization environment. Each hypervisor will ensure the reliability of the platform, the security and the performance. It will be very connected so that we can provide a full IT integration and orchestration. We can, for instance, use the Compass project from the LF Energy to configure very easily a substation. And then each substation will be, of course, linked to a supervision and control center. So let's go a bit deeper in the SEAPATH project. The goal of the SEAPATH, as I previously said, is to develop a reference design and industrial-grade open-source return platform. We want to open that to all new players, so it's very important to use open-source environment to do that. We want to host virtualized automation and protection applications, and we want to share a platform between multi-provider applications. And to do that, we want to be hardware agnostic so that we can use a regular server to test our applications. And of course, we want to combine performance that are required for this sensitive environment and safety with all the cybersecurity constraints we have to deal with. Let's go a bit on vision and technical concept. So the project is dealing basically with different layers. We have very high layers that you can see in regular data center systems with virtualization and high availability needs. We need also on the lower layers to deal with real-time and low network latency and minimal services and configurations. It's topics that you can find in a lot of different industrial embedded devices. And of course, we have to deal with cybersecurity, which is transversal to the project. So we checked the existing solutions, and off-the-shelf solutions exist and provide either high availability and virtualization platform, real-time or low latency platforms. But we didn't find one that mixed all of that. In addition, we wanted to have minimal firmware configuration, and we want to be able to configure the software used for different needs and different countries or architectures. So that's the reason why we decided to create our own Linux distributions. But also we wanted not to reinvent the wheel and to reuse open source components as much as possible. That's exactly what the Yocto project does. The Yocto project is a Linux Foundation project since 2011 and is very used in different areas: industrial, automotive, avionic, medical devices. The big job of the Yocto project is to basically create a custom Linux distributions based on system from source code. So it's very also agnostic of the hardware architecture. You can use the Yocto project for ARM architecture or for regular 64 bits architecture like we deal with on the SEAPATH project. There is an architecture of layers so that you can aggregate tons of open source components and you can decide which one you want to pick. And for instance, we are able to easily compile virtualization and high availability components for the SEAPATH projects. And for each component, you can configure and modify that for your needs. Of course, we want to be able to check and to patch all the CVE that could expose your product. And the Yocto project is done for that with some tools to monitor and some tools also to patch the CVE for each packages. So let's go a bit on the technical architecture and stack of the SEAPATH project. The Yocto project is used mainly to configure each components. There is Pacemaker, which is an high availability solutions developed by Red Hat and OpenSUSE, and it's of course open source. And its job is to create and manage a cluster of hypervisor so that you can handle any failures on one hypervisor. So for instance, we can define 2 or 3 hypervisors running VMs. If one of them is completely failing, for instance, due to a power shutdown, you can push and move all the VM into the other hypervisors so that you don't have any services shut down. Ceph is an open source component also developed by Red Hat, which is basically providing data replications thanks to file system distributed. KVM is the de facto virtualization system in Linux and is very suitable for real-time constraints into the virtual machines. We use Open vSwitch to provide a fully virtualized switch architecture so that we can use a software-defined network. And we can configure OVS to use DPDK, which is a kernel bypassing technology. Basically, it reduces the latency of the incoming and outgoing packets, bypassing the Linux kernel hierarchy model. On the platform, we have different CPUs that can be used for several usage. Some of them will be best effort CPUs. So CPUs will be shared between different VM. And we will have some real-time CPUs that we could allocate to one virtual machine so that we can ensure to reduce the real-time constraints. We'll do the same for the memory. And regarding the network interface, we could allocate one network interface directly to a VM, or we can share that with between several virtual machines, configuring that with Open vSwitch. On top of that, we will have different applications running: protection applications, automation applications, or OT monitoring applications. Thanks to the yocto projects, we can optionally include some tools for testing some development before pushing that in productions. So we would have some IEC61 tools or real-time test tools. And of course, like any Linux systems, we can use administrations for VM or containers. We can have platform monitoring, and we can monitor the fault and ensure to have a recovery system. So let's go a bit deeper now on how we can ensure reliability of the system by Robin. Thank you.
Thank you, Eloi. During the development of SEAPATH, we identified several issues with the traditional substation engineering approach that make it difficult to accelerate development of new technologies. The underlying reason is that due to the criticality of the environment, there is a natural preference for more traditional and well-tested technologies. We suggest using a continuous integration approach to accelerate development with the following reasoning. To speed up adopting new technologies in a critical infrastructure environment that is growing in complexity, a shift left is needed. Using containerization and virtualization combined with infrastructure as code enabling technologies such as Ansible will allow automated development, testing, acceptance, and production environments that provide confidence in the performance and reliability of a solution. If you doubt it, test it. Early testing, fail early, in such an environment will help to create a streamlined development process. Besides providing reliability, such technology will also limit startup costs for new innovations and therefore open up the industry to newcomers with new innovative ideas that would normally not be able to enter. SEAPATH therefore provides the following building blocks. SEAPATH recipes that allow for a customizable build process that supports traceability and automation, an automated build process by Yocto that includes unit tests that are run during each build, a build pipeline that allows further image validation and processing from the output of the build process, automated deployment using Ansible to ensure hardware is supported and platform configuration is in a defined state at all times, platform integrity tests that ensure the runtime performs as expected, integration tests that check if substation automation components such as an IEC 650 stack and related services such as PDP function correctly. Note, this is not conformance testing, merely functional. A real-time test bench that allows the platform and its application to be tested regarding real-time performance. Note that this list is not finite, as things like interoperability testing and site acceptance testing should also be performed, but are too use case specific to be addressed by SEAPATH. Now we will present you with some early results of the testing we have performed, so you know what type of performance to expect. Like any of the CI building blocks, these results should be reproducible by anyone who would like to try it. We tested interrupt latency on the host, as well as in a guest running on the platform. Here you can see the difference in performance to be expected between the SEAPATH preempt RT kernel with a maximum latency of 21 microsecond and a non-real-time kernel that can have up to 501 microsecond latency on the same hardware. Further details can be found on the SEAPATH wiki hosted by Energy. Here you can see performance in the guest image running on SEAPATH, where you can see that the latency in the guest with 149 microseconds is still much faster than the non-preempt RT performance. By no means does this test prove that the SEAPATH platform or any preempt RT can meet the deadlines needed by your specific real-time application. While we can provide the tools for validation, it will still require developers to do their homework regarding real-time application development and follow best practices such as disabling consoles, disabling hyperthreading, and configuring things like processor affinity. Besides testing interrupt latency, another important component for real-time applications in substation automation is the network packet processing performance and related to the subset of IEC 6250 real-time protocols, namely IEC 6250 goose and sampled values provide the real-time input-output capabilities needed in a substation and have stringent requirements regarding latency and packet loss. This performance relies, amongst others, on the networking hardware, the CPU configuration, the OS operating system, and the type of networking drivers used. As the whole system can be brought to its knees in terms of performance due to a bottleneck in this stack of technologies, it is important to be able to validate all individual components. Therefore, we provide a test bench that allows to generate packet streams with similar characteristics as IEC 6250 communication and allow to check certain edge cases. The idea of this test bench is to allow anyone to ensure a specific test setup has the real-time characteristics suitable for its critical application in the substation, to benchmark different hardware platforms to see if it can meet all the required performance criteria, understand the scalability potential of different setups, and validate the real-time performance impact of any configuration or changes made during development and operations. The test bench will require a physical test setup, as the hardware that the platform runs on matters, but the requirements for the measuring hardware is relatively limited. It mainly relies on a normal PC with a moderate to high-end network card that should support DPDK or Data Plane Development Kit, as well as certain timestamping features. For reference, I bought a suitable i350 Intel network card for about €70, and it allows me to perform hardware-based timestamp measurements with nanosecond precision on the test bench. The test bench contains an automated, configurable, and scriptable interface and several test applications that run on the SEAPATH platform to enable the testing of its performance. This is not unlike iPerf if you are familiar with it. As output, all measurements are stored in a separate folder and a test report is generated that can be compared with other test runs. The tests itself were inspired by RFC 2544, which is a set of test cases to test the performance of network equipment, but in our case have been adapted to check various relevant performance criteria of the SEAPATH platform. If anyone thinks we missed some relevant tests here, I'd be happy to hear from you. Here you can see an example of an automatically generated test report, in essence for frame sizes and timing that correspond with sampled value and goose communication. We check throughput, latency, packet loss, and burst rate. Besides that, we also check interpacket latency and jitter of a sampled value stream generated by the SEAPATH platform. And we perform a round-trip latency test of a sampled value stream into SEAPATH to trigger a substation protection function on the platform, and that in turn sends out a goose packet in response. This test can be repeated, injecting multiple back-to-back sampled value streams to test more resource-intensive scenarios as well. Please do not focus too much on the numbers displayed, as my SEAPATH setup is currently far from optimal, but it should provide a good idea of the type of tests performed. Please also feel free to run the test yourselves to see what kind of performance can be achieved on your hardware. I will try to publish some results when I have a better test setup myself. I'd like to conclude this presentation with a call to arms. As SEAPATH is a relatively young project, we'd be happy for people to contribute, but especially we're looking for end-user feedback, end-user applications, missing platform features, and if the test bench provides the right test to ensure SEAPATH performs as expected in a Substation environment. Therefore, feel free to raise an issue on GitHub, send a pull request after following our contribution guidelines, or get involved by joining the mailing list and/or Slack channel. Hope to see you there. Thank you for your attention.